So this lecture is really just an opportunity to make sure you see these slides. This sequence of slides, I think it's the next 10 slides. Where's my number? I can't find it. There it is. 10 slides are all big summary slides. So for instance, this one gives our big summary for the mechanism for SN1. It addresses all kind of little nitpicky details that you'd be responsible for. And so I want you to be able to go through and look at these kind of things. As I go through them, really all I'm going to try and do is nail down the big terms that should be coming out. So when you see SN1 or think SN1, you should be thinking carbocations. If you think carbocations, you should be thinking rearrangements. Okay, so those are your big pieces. I might also add as an addendum to this or as a secondary piece, when you see SN1, you're thinking the presence of nucleophiles. Actually, I don't like that. Don't do that. I want you thinking substitution. Okay, because the substitution is the big deal. I don't want you thinking nucleophile for SN1 because the nucleophile is important for the SN1. Okay, and you might also remember that you might have an extra acid-base step at the end of this one. So in our SN1 summary, this is kind of showing you that cation, again, summarizing some of those big aspects and some of those key points. Notice that we're actually seeing some hybridization showing up in this slide because we get that p orbital with our carbocation showing how the nucleophile can come in and attack from both sides. So it's again trying to draw attention to that. You notice you'll see some reference here that we're getting optically inactive products. Typically, when we're looking at our SN1, with our SN2, an attempt to put it all on one slide, theoretically again, when we're looking at our SN2, what you should be thinking as your key tip-off for your SN2 is immediately to backside attack. Okay. Hopefully, in addition to that, you're thinking, actually, it's a subheading there, steric hindrance, okay, which means inversion of stereochem. So stereochem becomes a bigger issue with our SN2. I want you thinking again with that S being substitution, but potentially more important for our SN2 is that N, because the nucleophile drives the SN2 reaction. Okay, so these are some kind of big word association games effectively that I want you to go through and do and have kind of at the back of your head, so that when you decide that you have an SN2 reaction, these things are kind of being pulled to the forefront. We've got our summaries for each of those four primary categories, our stereochemical issues, and kind of the benefits that we could potentially see with this. So in this case, no rearrangements. So deciding between which it was, SN1 versus SN2, we've got it all kind of listed out there. You'll notice that we have two blue sections showing up. We've got the substrate pattern and substrate showing up in two different places. Sorry, I thought that was a blue pen. Okay, Y showing up in two places. People tend to memorize the substitution patterns, tertiary, secondary, primary, zeroary, and can associate those with our substrates with SN1 and SN2. Do please, please, please be careful, particularly when it comes to SN1, because the primary driver of our SN1 is cation stability. There are multiple things that affect the stability of a cation, in particular resonance. As we already addressed as one of the complications of our SN1, which isn't on this list, we get our another favorite R word, rearrangements. So make sure that when you're thinking SN1s, those things are kind of pulling out and jumping at you. At the bottom of this, I've got my kind of quick walkthrough. I tend to look at officially the nucleophile first, then the substrate, to try and evaluate SN1 or SN2. If that doesn't work, I tend to move into looking at the solvent or other aspects or clues within the either reaction or question, or if I really got to dig into it, our answer choices. E1 summary, again, we've seen this for a while. When we see E1, what I want you to be thinking is we've got that E for our elimination. So as an elimination, make that pi bond. Okay. 1. So we're talking unimolecular, and unimolecular is going to mean our carbocation. Again, as soon as you see that carbocation, you should be thinking rearrangements. And because we have carbocations, we also need to be considering the possibility of resonance to go through and stabilize these things. After that, those are, I think, the big call-outs that I would pull for our eliminations. We've got the complications written down there. We saw those in our overview videos. Our E2, similar to our SN2. Do we have another? Nope. Similar to our SN2, that 2 is going to be a call-out for our backside attack. Okay. We don't really have a backside when we're talking about the elimination, which is the formation of that pi bond again. But what it becomes, because we're shifting away from this, is not so much a backside attack anymore, but everybody's favorite phase, anti-periplanar. Okay, so we have to still maintain that pseudo backside attack when we're running the E2 elimination. This is going to lead very forced regiochemistries behind our pi bonds, being cis, trans, or otherwise. There is that complication of the Hoffman elimination. To be honest, with the timing on when I'm recording this, which is out of sequence, I honestly can't remember if the Hoffman elimination is discussed in the slides. I don't think it is, so it makes me a little bit nervous. I may have to add a slide to address the Hoffman elimination. The Hoffman elimination is a quick review on that. You're looking at tertiary leaving groups, so sterically hindered leaving groups, and sterically hindered bases. Okay, if those two conditions are met, then the Hoffman elimination becomes an issue. Okay, and like I said, hopefully I will have a slide added in there talking about those. If you don't see that slide, then don't remind me, otherwise you may see a test question on it. Deciding between the E1 and the E2, the same kind of thing falls out as for the SN1, trying to establish those relationships on what things are good, what things are bad. Again, the E1, Again, with the E1, I do want you to be a little bit careful with your tertiary substrate pattern. Again, it's stability. That stability could very much lead to resonance. Okay, why is resonance not a big deal for the E2? It all happens at once. There's no carbocations, there's no resonance to really evaluate. Okay, so we get our complications thereafter and all that fun stuff. What I would highly encourage and recommend you do is on this very next slide, with my version of that table, is what we went through and saw on the past couple slides is a slide that looked at SN1 and SN2 and a slide that looked at E1 and E2. You should go through and build this chart, perhaps in your own document. That would be nice if you shared with everybody for the record, and fill in the big characteristics that you think belong for a nucleophile SN1, a nucleophile SN2. So what characteristics should get written into this? That was something I pushed and suggested that you try and do way back when, in the beginning of this unit, and I'm going to push it again here because generating that content on your own is probably going to be useful. These last few slides are a little bit oddly organized, but what these are trying to get at is, again, thinking about should we be doing substitution or elimination. So look at the strength of your nucleophile or base, because that determines the order. Your strong nucleophiles and bases promote the bimolecular type reactions. The weak ones promote the unimolecular type. Because nucleophiles and bases can be confusing, it's helpful to make sure you accept or outline their differences. So your nucleophiles are sharing electrons with something other than hydrogen, and your bases are sharing electrons with hydrogen. Because of the location of where those things are reacting, nucleophiles are reacting with electrophiles found in the middle of a structure. The nucleophile should be as small as possible so that it can sneak in and react with that electrophile. The base is reacting with hydrogens, which are all on the outside of the structure and so are relatively easy to get access to. I don't care the size of the base. So a really big negatively charged structure, okay, molecule, won't be able to act as an electrophile, which means it can only act as a base. Okay, so those sterics become kind of a big deal. Substrate structure. We've got our summaries kind of here. The primary halide is fantastic because that really does tend to push your SN2 reactions. Your secondary halides are a complete S show because every mechanism works with a secondary leaving group. And then your tertiaries are not much better than the secondaries, but they do at least eliminate the SN2 because they're too sterically hindered to allow for a backside attack. Solvent, our protic favors SN1, aprotic favors SN2, and if you can, avoid trying to use the solvent to decide which elimination mechanism to run because it's not useful. Instead of you looking at the solvent to decide substitution versus elimination, look for temperature. Temperature is a red flag, kind of no pun intended, that will suggest that you have an elimination. And so within that, you now have all of the bits and pieces that make up really just chapters 8 and 9. Okay, so 6 and 7, you would still need to go back and watch those videos and address those. But this, in 10 minutes, you got all of the content that you would then need to be able to apply for your substitution and elimination chapters in whatever that is, 8 and 9. Okay, hopefully that was useful. Really, what might be useful is if you just rewatch this and mute me and just look at the words on the screen. Use these to kind of help your way through solving questions.